So let's talk a little bit about the, the ancient Greek model. It was really, I call it the solar system, which is the sun and the planets and stuff, but it was really their model of the universe. This is also known as, AKA, right, also known as the Earth-centered model, or the geocentric model, or the Ptolemaic model. All these are sort of synonyms for the model that has the Earth at the center of the so-called universe, what they thought was the universe at the time, right? And so I'm just going to draw a picture of this, right? And we're going to have to sort of try to understand it from our vantage point. And so in this picture, they had the Earth. This is not going to be a scale drawing, okay? They had the Earth at the center, and then the planets go around it. So, you know, out here somewhere is Mars. Right, here's Mars going around. But Mars engages in that, retrograde motion, right? And so they have to have a little epicycle on Mars. And so here's Mars. Maybe I'll draw Mars red. What do you think? And so here's Mars. And it's going around this way. The epicycle centered here, this is just an imaginary circle that Mars is going around on, while this circle is tracking this way in the along what we would call the orbit. This orbit is called a deferent. And the little circle here is called an epicycle. And when Mars is over here, as it goes around when it's over here, from the Earth it looks like it's backing up, because this is going around slow and it's going around a little faster on here, and so it actually looks like it's going backwards. And that's how they explained, the ancient Greeks explained retrograde motion with these deferents and epicycles. And they tried to get Mars to be in the right position in the sky, tried to develop ways to predict Mars's position and so forth, just as we do with our more modern models. They were trying to do basically the same thing. So that's just a quick picture that we've already talked about a little bit. So let me talk about the real model for a second, and then I'll come back to this one. So what really happens is that we have the sun at the center of the solar system, and I'm going to put the Earth somewhere. So like I want to draw some inner planets. So let's put the Earth over here. So I'll draw a little blue Earth, right? Here's the Earth, E. Right. Well, we know that actually between the Earth and the Sun, there are two planetary orbits. Here's Mercury. This is Mercury's orbit, and we can just put Mercury anywhere in its orbit. Here's an M for Mercury. But another inner planet is Venus, and its orbit is between ours and Mercury's. And so, so here's Venus. I'll draw Venus over there somewhere, right? And these guys orbit at different rates. All these guys orbit at different rates, and so anybody can be in any position at any given time, right? You notice that if you're watching from Earth, right? Let's say so all the planets orbit in the same direction. So let's say we're looking at it down from the top, and they're all orbiting kind of this way, right? The inner planets, the more in you are, the faster you go. And so Venus is going to pass us by here. Mercury's going to pass us by a little more quickly. If you notice, from wherever the Earth is, Venus or Mercury can only be about that far away from the Sun as an angle, right? You'll never see Mercury out this way. Sorry, you'll never see Mercury on the other side of the Earth, because it doesn't get there, and it doesn't get much farther away than this. Like this here might be the maximum angle you see. And when it's at that angle, which we'll talk about later, that's called the angle of maximum elongation. So if they're orbiting this way, all the planets are kind of circling this way. The Earth is anyway. And so you can sort of ask yourself, well, where would you be standing on the Earth if it was noon, right? And so if it was noon, the sun is kind of straight overhead. And so, again, this is not a scale drawing, but that's where I would be at noon, right, with the sun directly over my head. This would be sunset for me, right? Over here would be midnight, and over here would be sunrise. Right? And so as the sun begins to set, when the sun goes below my horizon, there's just a short time before Mercury is below my horizon, assuming it's here, right? If Mercury is down in this half, it sets before the sun does, right? But then when I came around, it would rise before the sun rose, right? Because as I came around to this side, I'd first be seeing along this direction, and then along this direction, and so on. And if Mercury was down here somewhere, it would rise before the sun would. And so both Mercury and Venus are within some angle of the sun. And that's an important point because the Greeks had to deal with that. And this is one of the little stories that lets us know that the Greek model is wrong. Galileo sort of did this, and that the sun-centered Copernicus's model is right. So let me pause here for a second. So here's a picture sort of the Greek model. And you can sort of see here the Earth is at the center and the moon's going around the Earth. And then here's the sun going in a circle around the Earth, along with all the other planets and their little epicycles, right, kind of doing what they're doing. And notice that they have Mercury and Venus kind of doing a circle, tracking this line that connects us to the sun. So here's a line connecting us to the sun. Venus and Mercury just stay on that line and do circles while tracking along with the sun. And so this will, as the sun moves around, Venus and Mercury track with it. And that's why they're always within a certain angle of the sun. This is a fairly complicated drawing, right? And then the stars and the celestial sphere are sort of back here, out beyond the solar system. And so that's the Greek model. And it's not, by the way, that the Greeks didn't consider a moving Earth. So if we go back to the sun-centered model, the so-called heliocentric model, and we put the Earth going around the sun, the Greeks actually considered this model. So let me draw a little Earth here, right? And then out here somewhere are all the stars on the celestial sphere, right? I'm just going to draw, I've got a reason for this. Let me just draw some more stars. So the Greeks considered the possibility that the Earth could orbit the sun. And it was suggested by a guy named Aristarchus around 250 BCE. He was the guy who made all the other measurements besides Eratosthenes measured the circumference of the Earth. But this guy was the one who figured out the size of the moon, the distance to the moon, the size of the sun, and the distance to the sun. And once he figured out that the sun was bigger than the Earth, he thought, well, wow, maybe the sun's at the middle and the Earth goes around it. And that would explain retrograde motion and all these things, all the stuff that Copernicus came up with later. It's right in the glare, isn't it? I'll put it up here, 250 BCE. BC, for some reason I can't make that work. E. But here's the thing that the Greeks got wrong, but for noble reasons. If the Earth is here, say as it goes around the sun, and you look at this star, then from here, this star kind of lines up with that one. But later on when you're up here, this star kind of lines up with that one. And so closer stars and faraway stars are subject to parallax. It's like when you hold your thumb up and you look at something, and then you with one eye, and then you close that eye and open the other eye, and the thumb appears to move against the background. Nearby objects appear to move faster than farther away objects, and so you get this parallax effect. It's the very effect we get that results in retrograde motion. It's the illusion that something appears to be moving backwards, and they thought they should see it for these stars. And they didn't. If you observe these stars, you don't see any of that. And so Aristotle in particular concluded that the Earth has to be at the middle for that reason. Otherwise, we would see parallax on these stars, and we don't. And the fact that everyone thought you should be able to detect motion. If the Earth is spinning and traveling and doing all this stuff, we would feel it. They were wrong about that also. It turns out the reason you don't see this effect is because the stars are way, way, way farther away than they imagined. These stars are trillions of miles away, and this distance here, this motion here, is millions of miles or hundreds of millions of miles. It's just a tiny, tiny fraction. It's like looking at a tree that's 2 miles away and then shifting an inch and expecting some change in its position when you're looking at it from very far away. And so that's where they got it wrong, and it's understandable that they would get that wrong. They just way underestimated how far away the stars are, and so they kept the Earth at the center of the solar system, and they kept the and they gave the diagram that we've been talking about. There. So let me just talk through a few of these here for a second. So Aristarchus did a bunch of these things. I just talked about that. He measured the size of the sun. And then in around so at the end of the Greek Empire, or at least the golden era of the Greek Empire, Ptolemy, around 150 of the current era, 150 AD, compiled a 13-volume almanac called Almagest, covering all of astronomy, in which he detailed these models, the Earth-centered model, and how to locate the positions of things. You can imagine it must have been very complicated, because it was all these deferents and epicycles that don't exactly reflect reality, and they were to be used for hundreds of years, more than that, maybe over 1,000 years, and it became increasingly inaccurate. And so sort of the birth of modern astronomy began in 1,000 years later, or more than 1,000 years later, in the 1300s, when we began to have build ships that could travel around the world and needed to use astronomy for locating themselves, for example, for direction finding and things like that. And it was very useful to know where the planets should be at different times. And Ptolemy's model was getting extremely inaccurate after all that time. It was inaccurate to begin with. And the scientific community and the technical people needed a better model. No one wanted to go through all the work Ptolemy did to create the volume he created, because most of the people who knew how to do that stuff believed it was wrong, that the model was wrong. And so Copernicus came along, Nicholas Copernicus came along, and he lived from 1473 to 1543, and he developed a model kind of by himself called the heliocentric model, or the sun-centered model, and he believed it was better than the Earth-centered model. It explained the retrograde motion just as we did earlier, much more precisely. And the explanations for the orbits of the various planets were much more, there we go, much more realistic, I think is what I'm looking for there. So let me just, this is a drawing from Copernicus's book. And really he's got everything sort of in the right spot. He has the sun at the center, and then Mercury, Venus, Earth, and then Mars, Jupiter, Saturn. And I think this is the celestial sphere out here. And so it's got the moon orbiting the Earth. And he's got it all laid out right. The only thing that Copernicus got wrong, and we'll talk about that in the next chapter, is that he had everything moving in circles. Throughout history, people thought the heavens were perfect, and so the perfect shape is a circle, and so everything was round, and all the orbits were circular. It's easy to believe someone would make that mistake because everything is very close to circular anyway. It's just not quite. And so he died in 1543 and literally published this on his deathbed. He sent it out. He had it for a long time and was afraid of the consequences of publishing it. But ultimately he did. And so other people got to see it. And one of the people who got to see it was Galileo. And Galileo immediately jumped to some conclusions that could be drawn from the difference between the two models, and one of them was the phases of Venus. If Venus orbits the sun, as is shown in this picture, then viewed from the Earth, sometimes Venus would be on the far side of the sun, in which case it would be mostly lit up. We call it gibbous when it's more than half lit. Or it would also be crescent when it was on the near side of the sun. And so you would be able to see it in all phases. Let me just jump back to the Greek picture. Venus is always lit on the sun side, and so you would never see a gibbous Venus in the Greek model. And so Galileo made it his life to shoot down Greek models, and this is one of his examples. You can sort of see the two pictures here. The top one is the model that Galileo said you would see if Copernicus was right, and the bottom one was the model if the Greeks were right. And Galileo was one of the first people to build a telescope and was the first person to aim it up in the sky, and sure enough he saw the top picture and not the bottom picture. And so Galileo really showed that the Copernican view had to be right. There were other little pieces that Galileo put together. For example, there's a picture of Galileo. There's his telescope. This is a picture, this is a hand drawing that Galileo did of Jupiter. So the circle is Jupiter. These are dates on the left in Italian. The circle is Jupiter, and the little stars around it are moons, Jupiter's moons. We know that the stars, the actual stars in the sky are fixed, at least for human lifetimes. But Galileo showed that these little objects from day to day were flittering around either side of Jupiter, in other words, orbiting Jupiter. And this is clearly a violation of the Greek model where everything had to orbit the Earth. And so Galileo was collecting ways that the Greeks were wrong. And so the phases of Venus and the moons of Jupiter were two ways. He also saw through his telescope rocks on the moon and mountains and craters on the moon. These were inconsistent with Greek philosophy as well, which said everything was perfect spheres. And he saw sunspots on the sun with his telescope. Also inconsistent. The sun was supposed to be a perfect sphere. So Galileo spent a lot of time shooting down the Greek model and was pretty good at it. Let me just pop back over here for 1 minute to my notes and make sure we're not missing anything. So the heliocentric model is the sun at the center, and that's what Copernicus came up with. I'll remind you that Aristarchus, the ancient Greek, came up with it also. They just didn't stick with it. Galileo advanced the heliocentric model by showing the phases of Venus and showing their moons orbiting Jupiter. So in the next chapter, we're going to talk about a little more physics. We're going to get to a little more Galileo and a guy named Johannes Kepler and Tycho Brahe and Sir Isaac Newton and their contributions.